Okay, yes. Welcome to review session 8. Class has kind of reached the second half of the class now where you've graduated from DC circuits and are moving on to AC circuits, which is more complicated and there are more components, but ultimately it's not that much worse if you know what you're doing. I'll talk about two main things this review session, which is RLC circuits and then frequency domain stuff. So frequency domain slash impedance. Okay, so to start, RLC circuits, RLC stuff. So RLC, as the name implies, you have a resistor, an inductor, and a capacitor. You know how to do stuff for just inductors or just capacitors at this point. However, when you start bringing them all together, it can get a bit more confusing. This is because the inductors and capacitors kind of like fight each other in a way that will become more apparent when you see their impedance. But basically, what you end up getting is unlike a normal RL circuit or an RC circuit where you have some kind of exponential behavior that looks like this from like an initial value to something else. Instead, with RLC circuits, you get one of three behaviors, which is called overdamped, underdamped, or overdamped, critically damped, which is kind of just between them, and underdamped. I don't know why I wrote two Y's. Let me mute something here. Okay. Or underdamped, overdamped kind of just looks the same. Critically damped is that, but like faster. And then underdamped is when it like overshoots and then wiggles back to where it's going. Um, I think diffie is a correct for this class, so everyone like should kind of know what this is. I forget if it's a correct. I don't know. A lot of you probably have to take diffie and you're either taking it now or you'll take it next semester. So this stuff should sound familiar. And basically, the table that was given to you, which I can pull up right here, ignore that. Oh God. Okay, there we are. This table here, as you can see, is basically they took differential equations that describe um the inductors and capacitors and solve them for you. And it's just a bunch of complicated equations that you can then plug your numbers into and it'll give you the solution. So if you're curious about how all this works, it's just a bunch of differential equations, but for the purposes of teaching this course, and I guess for the purposes of the people making the textbook, they solved all the equations for you and put them here. Yeah. So I'm not really going to go too in depth into this because it's really just like a pain and you'll never have to do this again really once you learn about frequency domain and everything's a lot easier. Um, but this is like something that's good to know, I suppose. Um, yeah, I'll do like one or two examples for this, but the general format is you have your table here. So you're going to want to start by simplifying your like T is greater than zero circuit into one of these two forms where you have your voltage source usually with the three things in series, or you have a current source with the three things in parallel. And you want to like combine all of them into one thing just so that it makes sense. Then you're going to, using these equations down here, you're going to calculate your alpha and your omega naught. I forget what alpha is. Omega naught is like the resonant frequency, which you'll learn more about if you're an electrical engineer or a BME major when you take signals and systems. Also, actually, maybe like everyone learns that. I'm not really sure. And this is maybe like the damping factor. I think that's the damping factor. That feels right. Um, but basically, you see how these compare to each other, and based on that, you get one of like the three rows here. So if you look at this, right, overdamped, you have two terms that will usually decay to zero. Here you have like one term that will decay to zero, and then here you have sinusoids. So that's why here you get like kind of like a that, here you get that but a bit sharper, and then here you have sinusoids. And if you look, the sinusoids are also decaying to zero. So that's the same in all the cases. The difference between series and parallel is that for series, all these equations are in terms of the voltage on the capacitor. And for parallel, all of them are in terms of the current through the inductor, right? Cool. Um, so basically, using the same methods you've learned in this class, where you remember that, okay, at long time or like at DC, whatever you want to think of it as, an inductor is a short circuit and a capacitor is an open circuit. You use that to find your VC of zero and your VC of infinity. Over here, you'd use it to find your IL of zero and your IL of infinity. And then you plug your stuff into all of these equations. You know how to use a calculator. It just takes a while. And then you find your two coefficients and then you plug it into this equation. And it just takes a while, but it's really straightforward. Hopefully you all know how to plug numbers into equations. And yeah. So there is one caveat I will point out. If you notice here, it has like these VC of zero and VC of infinity terms, which you're used to. You know how to find those. But then for this IC of zero and VL of zero, right? That's not what you're used to. And what that is it's really like IC of zero plus. So if you remember, let's say we had like a 5 volt source here, and then it switched to, this is like kind of a bad example. But let's say you had a 5 volt source here, and then it switched to something else. I don't know. But basically, the point here is that the current through this capacitor could maybe change instantaneously, since the current through a capacitor is not it's the voltage across the capacitor that can't change because it has to be differentiable, right? And you have to have like the charges flowing on and off the plates. Whereas the current could technically change instantaneously. So what this is saying is that this term, for a lot of questions, it might end up being zero. Like here, if you have an inductor in series, um, then the current through the inductor can't change instantaneously. And if these two are in series, then if the current through the inductor can't change instantaneously, then the current through the capacitor couldn't change instantaneously either. So this could just be zero. But there are cases where it will be an actual number. So like, I guess a good example of that would be like, let's say your circuit was like this, and then all of a sudden at time equals zero, you were connected to a resistor, and or at when time equals zero plus, you're connected here. Then all of a sudden, for t is greater than zero, let's say t is greater than zero, this little bit moves down, right? In this case, for time is equal to zero minus, when you're in the state for a long time, IC of zero minus would be zero, of course, because the capacitor is open at DC. But then the moment this switch moves down, all of a sudden you have I equals V over R flowing through here, right? And that would be what you fill in for this IC. I don't know, like, I don't know if that'll end up being relevant on the quiz, but just think about that. It might come up in one of the examples I do. I don't really remember. And then similarly, you have the same thing, but in reverse for the inductor, where this voltage across the inductor, uh, this can change instantaneously. It's just the current can't change instantaneously. So it's the same thing, just in reverse. If that comes up, I'll go over it. Just keep that in mind. Try to figure that out. And then also, like, the signs for these have to be with respect to the passive sign convention. So, like, if the current's flowing here and it's flowing from positive to negative, then that would be a positive current. But if the current all of a sudden started flowing in the other direction and we defined VC as that way, and then we had current flowing that way, then that would be a negative current. So just things to keep in mind. I really don't know if it'll end up mattering. Depends on what kind of question you're given, but it's a good thing to think about. So that's that. I will go over examples of this, but like really it's just plug and chug. It's just annoying and takes a while. Okay, next up, I will talk about the impedance and frequency domain. So this is relevant for AC circuits. So this is when your voltage sources of are no longer DC. It's going to look something like A cosine omega t plus theta, right? So what we have here is an amplitude, a frequency, and a phase shift. They use the phase shift in degrees just because kind of makes a bit more sense to think about intuitively if you have it in degrees rather than like having it be in terms of like matching it to the units there. So we just leave it in degrees. And basically what happens then is your circuit will respond in a certain way to a sinusoidal input. So if we have some sinusoidal input here, and you have a circuit with like a bunch of components, that's a resistor, trust me. Um, uh, sure, and we want to say, okay, what is the voltage output here, right? Well, if we want this to be our V out, what's going to happen is capacitors and inductors respond to sinusoidal signals in interesting ways, and it's dependent on the frequency. If you think about it, right, a capacitor takes time to like charge and discharge the charges. So if we have a sinusoidal like coming in, then it'll push some charge in and push some charge out and then push some charge in the other way. And you can represent that as kind of a resistance. And that's what we'll go into here. So for a capacitor, okay, wait. And the way that we do this is we do it with complex numbers because it makes the math a lot more like elegant, as they say. It makes it a lot more straightforward. And to do that, we're using phasors, which is a way to represent the sinusoids as a complex number. So, for example, in this case, this would be turned into a e to the j theta. So we ignore this omega when turning it into here because the assumption is if I'm driving this with some frequency here, then the output will end up having the same frequency, right? It'll have a different alpha won't be the same and the theta won't be the same, but it'll have the same frequency. And then that frequency comes into play because what we do is we take our capacitors and we take our inductors and we say, okay, we're going to say Z, this is the symbol for impedance. It's like resistance, but in complex numbers. So the Z of a capacitor is 1 over, oh, and J is just the square root of -1. Since I is already used by current in electrical engineering, we use J instead. So don't get confused about that. But the equivalent impedance of a capacitor is 1 over j omega c, which is the same as -j over omega c. And the impedance of an inductor is j omega L. So, like, if you don't take away anything else, remember this, right? What this is saying is as the frequency goes up for a capacitor, the impedance goes down, or you can think of it like the absolute value of the impedance goes down. As the impedance goes up for an inductor, the absolute value of the impedance goes up. So what that's saying is at high frequencies, like you don't really need to know this for this class, but if you're an electrical engineer, this will help you in the future. At high frequencies, an inductor or at high frequencies, a capacitor acts as a short circuit, as like a wire, whereas at high frequencies, an inductor acts as an open circuit. So like an inductor will block high frequency signals and a capacitor will let high frequency signals pass. Yeah. Now, what we can do is let's say we had some capacitance value here, some capacitance value here, some inductance here, and some resistance. Oh, and the other thing is that for a resistor, it's just the resistance, it's purely real. So for a resistor, or basically once you calculate all of these for all your components, you go back to your circuit and you say, okay, now I have a voltage source with some complex voltage. I have a capacitor, which we're now going to represent as like a box just to generalize it a bit more, to show that it's like we're not really thinking of it as a capacitor anymore. And now this will have a value of -j over omega c. This will have a value of j omega L. This will have a value of R still, and this will have a value of -j over omega c2. And what we have now is we just have a circuit. All of the values are complex numbers, so the math is a lot harder, but you can still use literally all of the exact same equations and all the same tools you've learned in the first part of the class. So this, right, is kind of the same as if you just had a voltage source with some voltage, or you just had a circuit with some voltage source, and three resistors, right? Pardon my horrendous drawing here, but it's basically the same as this. It's just now instead of real numbers here, right? Now you have imaginary numbers here. So this is basically just your algebra got a whole lot harder, but the process is still exactly the same. That's kind of the gist here. Um, I would recommend reviewing your complex algebra. Like, make sure you understand how imaginary numbers work. Um, One thing that's good to know, which is very important actually, is that the whole reason we do this, e to the j theta is equal to cosine, uh, yeah, it's cosine theta plus j sine theta. What that's saying is like in the imaginary plane, hopefully you've all kind of learned this, or I don't really know when you're supposed to learn this in math class, honestly, but I don't know, look up some YouTube videos about imaginary numbers. What we're saying is this is a way to write this. If you think of this on like the unit circle, like it's sine and cosine, right? We have some imaginary number, theta, and this would be like A, sure. I'm kind of skimming over this real quick, but it's good to think about this in like the complex plane. So if we have our sinusoid with a e to the j theta, that falls on the complex plane like at this point. And if you look at this and look at this, that's how you get that. So that comes in handy when you're like converting between the two. And yeah, I'm not going to go too in depth on imaginary numbers because hopefully you all already kind of know that. I will say I do have a video on this YouTube channel or on my YouTube channel from like a semester or two ago going over how to do complex math really easily in like a TI-84. So I would recommend watching that. Um, yeah, I'll put that here. Watch the imaginary. I'll post this as well. I think it's still good. It'll make your life a lot easier. At the very least, use it to like check your work. But the main takeaways from this is that when you have a circuit with a sinusoidal input, right? Well, all you do to solve the circuit is you turn your inductors and capacitors into imaginary numbers, and then your circuit is exactly the same. If you wanted to put these two in series, you just add these two numbers together. If you had two things in parallel, like it's still the Z1 Z2 over Z1 plus Z2. It's just now this math is harder because these are all complex numbers. But it's still all the same things work. Just try to keep that in mind. Nothing changes, it's just imaginary numbers now. Other than that, it's still exactly the same. Oh, and then once you do all that, you'll end up getting like a kind of out of space here. But let's say you do all that and you end up getting some voltage out here, right? Let's say your V out is you have it in the form, I don't know, A plus JB, then you can convert that back into a e to the j theta form, where a is going to be the square root of a squared plus b squared. If you think about this down here, that makes sense because it's like sine and cosine squared, Pythagorean theorem. Hopefully you understand what I'm saying. And then theta is going to be the inverse tangent of b over a. Again, it's like trigonometry. You got it. So you get this, and then you would turn this back into your final output of like a cosine omega t plus theta. Yeah. One other thing, they might give you the question in sine form. All you need to know there is that sine is equal to, I think, cosine theta plus 90 is it plus or minus?
Minus.
Minus, thank you. I always forget that. There you go. Yeah, because it's sine of zero is zero, and then cosine. Oh wait, no, that doesn't work. That's yeah, cosine of that's a bad example. Wait, sine of 30 is one half, and yeah, cosine of cosine of negative 60 is also 1/2. Yeah, okay. So keep this in mind. If you ever get something in sine, just subtract 90 degrees from the theta and then use that. Cool. Now I will do practice problems for the remaining half hour. Okay, I'll start with just like a RLC question. Here's a pretty basic RLC question. Yeah. So, yeah, okay. 2.5 Henries, 500 ohms, and 2.5 microfarads, 16 volts. So here, it's not a sinusoidal input, right? So you can't use the frequency domain at all. This is where you have to use that big equation table. Um, and it's asking you to find the voltage across the 500 ohm resistor. Yeah. So to start, we have to find, let's see. Yeah. So to start, we want to find just like for all of the equations, it's good to find VC of 0 minus, IL of 0 minus. And for that, we can look at this and pretty straightforwardly just see that this is going to be 16 volts, right? Because, that's the only path and it's a short at DC, that's what you'll get. And since there's no current flowing here, IL of 0 is going to be 0 amps. Um, so then for T is greater than 0, now we're going to have this be closed, right? And now if we are to source transform this, right? Let me make sure I'm thinking about this right. One sec. Yeah. So once we're here, as you see, the capacitor and the inductor are in parallel. So we're gonna want to end up getting everything in parallel so that we can use this equation, right? Because if these two are in parallel, we can't get them out of being in parallel. So that means we need to get the rest of the circuit to be in parallel as well. So here we're going to turn this into, okay, the current is going to be 16 over 500, which is 0.032 amps. So we end up with a current source, a resistor, capacitor, and an inductor. And this is 0.032 amps. This is still 500 ohms. This is still 2.5 microfarads, and this is still 2.5 henries. And now we're going to look at this and say, okay, um, we have to figure out now what equation we want to use, right? So by that, I mean, we know that we are in parallel world, right? So we have to figure out our omega naught and our alpha, and then compare them to figure out which of these equations we're going to use. One thing I will also point out is that on the quiz tomorrow, you will be given this table, but all of these will be crossed out, or they'll be not shown, and this won't be here, and this won't be here. So you have to know which equation corresponds to which one, right? So you're gonna, like I said, you're gonna be given everything. You're gonna be given all the equations, but they just won't be labeled. So you have to know which is which. Just take some time to memorize that or think through it. You know that the ones in parallel are going to be dealing with the current, and the ones in series are going to be dealing with the voltage. And then underdamped is going to have the sine and cosine, and like yeah, you can probably figure it out. Just keep that in mind. They will not be labeled, but you'll have all of the numbers. So going back, uh, we have that our alpha for parallel is 1 over 2 RC, which is going to be 1 over 2 times 500 times 2.5 times 10 to the negative 6, which gets us 400. And our omega naught is going to be 1 over the square root of LC, which is 1 over 2.5 times 2.5 times 10 to the negative 6, square rooted, which gets you also 400. So this question has been designed very nicely so that alpha actually equals omega naught, which means we're using the critically damped. I did not spell that at all right. Critically damped. So we're using that equation set in the middle. Let me copy this over. Okay. So we're using the and since it's in parallel, we're using this. You see? So now, what do we have here? Well, we now need to just find all of these numbers. So if we look at this, first let's find what IL of infinity is going to be. If we look at this, right, as time goes to infinity, this will act as a open circuit and this will act as a wire, right? Open circuit, let me use my laser pointer actually. Open circuit and a wire. If there's a wire here, all the current will end up flowing through the wire and skipping the resistor, right? So we know that our IL of infinity is going to be 0.032 amps because it'll just get all of the current from that current source. Now, um, let's see. Okay. Yeah, so if we want to find our parameters here, we see B1 equals IL of 0 minus IL of infinity. Since the current through an inductor cannot change instantaneously, because that is the whole point of the inductor, we know that IL of 0 is the same as IL of 0 minus. So this is going to be 0 minus that 0.032 that we just found. So we know that B1 is equal to negative 0.032. Now B2 is going to be 1 over L VL of 0 plus alpha times B1, basically, right? And now this is where I was saying that thing at the beginning about the voltage. So if we look at this, what is VL of 0? In this case, VL of 0, right? So that's going to be the voltage here because the current's going down, so a positive voltage would be having a drop in the direction of current. The voltage across here is the same as the voltage across the capacitor, right? Because they're in parallel. And the voltage across a capacitor cannot change instantaneously. So even though at time equals 0 minus, we might have had 0 volts here, right? Once this switch closes, now it's connected to the capacitor, right? And the capacitor has 16 volts over it, right? Because it's in series with it, or it's connected to here. So once we connect the 16 volts of this capacitor to the inductor, all of a sudden, now the inductor also has 16 volts over it. So at time equals 0 minus, right? The IL or at time equals 0 minus, the voltage across the um, inductor was 0, right? Because it wasn't connected at all. But then the moment that switch moves, all of a sudden this is come on. At once the switch moves, the voltage across that inductor becomes 16 volts because it's directly connected to that capacitor, which has 16 volts on it. So all that tells us is that this VL of 0 is 16 volts, right? And we know L, so 1 over 2.5 times 16 plus alpha, which we found to be 400, times negative 0.032, which we found in the previous part. And we end up getting negative 6.4. Cool. And now we can plug in our number. We can plug everything into that equation they have at the top there. IL of t equals B1 plus B2 B1, so negative 0.032 plus B2, so I'll write it as minus 6.4t e to the negative 400t, right? Because that's alpha, plus IL of infinity, which is in that case going to be minus 0.032. And that would be amps for time is greater than or equal to 0. However, it was asking us ultimately to find oh wait, did I miss something? Oh. Oh no, I didn't. We're good. Okay. So, but we want to find the question, I might have mentioned this. The question was asking for the voltage of the resistor, right? So that means we should probably also find the voltage of the inductor, right? Because if we look at this original circuit, so basically we did this source transform in order to learn things about the inductor. However, the real circuit we were interested in is this original circuit with this in series. So now that we found stuff about the inductor, we have to go back to this original circuit and figure stuff out about it. But before we do that, if we look at this, right, if we were to figure out the voltage across this inductor, then we know the voltage here. So the voltage across the resistor would just be 16 minus the voltage across the inductor, right? Just like a KVL, if it goes up 16 here and then it goes down VL here, then the difference here would be 16 minus VL. So to find the voltage, right, the voltage of an inductor is equal to L di dt. So we take the derivative and multiply it by the inductance. And so that's 2.5 times the derivative of that. You have to do some chain rule. I'm going to skip the math and just write the answer because hopefully you all know calculus. 16 plus 6400t e to the negative 400t. What this is saying is that originally it has a really big voltage of 16, and then it eventually will decay down to zero because this will decay faster than this goes up. So it might actually look something like 16, like, I don't know, but it'll end up going down. Not exactly sure how that'll look. So now we go back to our original equation or our original circuit. It looks like this. And for time is greater than zero, the inductor is connected directly. And we know that this voltage here is that, right? So then the voltage across this is going to be 16 minus VL of t. So the voltage across that resistor is going to be 16 minus 16 plus 6400 t e to the negative 400 t and volts for time is greater than or equal to zero. So that was a lot of work. It is confusing. I'd say this is probably the most annoying quiz of the class, just because like doing these questions is so annoying. It's just a lot of plug and chug and making sure you don't mess up a sign somewhere or something like that. But that's kind of how you do it. If these numbers were slightly different, right, then we would have to use a different equation. Like let's say omega naught was 200, then we'd have alpha is bigger than omega naught. Then we'd be using these equations instead, and you have to find this like S1 and S2. But it's still all the same stuff. It just takes a while. And since it takes a while, that means they can't really put a very complicated one on the quiz. This is as complicated probably as you'll get, I would hope. I actually have no idea. Maybe they're going to be mean to you. But I would assume that they wouldn't put something too complicated because you have to have time to finish the question. But yeah, so that's maybe what half of your quiz would be. Depending on time, I'll try to find a series one, but I'm gonna do a question on impedance next because that feels like I should do that. Um, let's see. Yeah, these ones seem okay. Um, yeah, okay. This is like a really straightforward question. And this is just kind of to show that your frequency domain stuff is really exactly the same as your time domain stuff, just with imaginary numbers. Okay. 1 millifarad, 40 millihenries, 6 ohms, and 100 millihenries. And then this is 7 sine 100t plus 20 degrees. Okay, volts. So the first thing that we're going to do, oh, and the question is asking for what is I of the 2 ohm resistor of T. So the first thing we're going to do before we look at anything is we're going to turn this into a cosine because that's what we do because cosines are better. So you just subtract 90 from this 20, so it's going to be minus 70 degrees. So we're doing that first. Now, we're going to turn everything into the frequency domain because that makes our lives kind of it's just easier. It's the only way you can really do this, unless you want to solve a bunch of differential equations with sines and cosines, which you're not doing and you did not learn how to do. So, yeah. So we're going to take this circuit and we're going to turn it into the frequency domain. So first off, this voltage source will become 7e to the negative j 70 degrees. Wow. Our 100 millihenries. So remember, z of L is equal to j omega L. So for 100 millihenries, we're going to have, I'll say Z1 equals J times 100 times 100 times 10 to the negative 3. Can I do that in my head? I think it's 10J. That feels right. Uh, for the resistor, it's still the same. So I'll write this in. This is 10J. Then we have 6. Oh, and these all have units of ohms. It's like imaginary ohms. Just don't think about it too hard. It does make sense based on like what imaginary numbers are if you think about them, but just just know that you can in fact add them together. They have the same unit. Z2 is going to be J100 because J omega is 100 from here times 40 times 10 to the negative 3, which is 4,000, but times 10 to the negative 3, so we get 4J. And then for the capacitor, so I'll write that here, 4J. And then the capacitor, if you see here, I'm leaving the drawings as the actual inductors and capacitors. It really doesn't matter as long as you keep the values right. This is, of course, going to be 2 ohms. I'll write ohms for all of these for fun. Also, like sometimes they'll write it as J4 or like J10. It really doesn't matter. Whatever it makes the math easier for you, just do that. Then for the capacitor, it's going to be uh I'll write it as ZC equals 1 over J omega C, but it's better really to think of it as negative J over omega C because you really want this to be in the numerator for doing math later. So this is going to be negative J times 1 over 100 times 1 times 10 to the negative 3 because it's 1 millifarad. So we're going to get point, this is negative J times 1 over 0.1. So this is negative 10J. Hopefully you all see how I did that. So what we end up with here is kind of a pretty nice, straightforward set of numbers, you know? Like all of these are integers. It's pretty chill. I guess they're not integers, but all of the coefficients are integers. So now, okay, it was asking us originally to find the current through that 2 ohm resistor. Since all of these are in series, the current through that 2 ohm resistor is the same as the current through everything. So what that also means is if I were to take all of these in series, right, and find the current through them, then that would be the current through the 2 ohm resistor, right? So what we can do, since they're all in series, and since I've said many times now, once you have them in once you've turned them into impedances, you can treat them like resistors. What we're going to do is we're going to just combine all of them into one impedance box thing. So let's call this Z equivalent, and it's going to be equal to just all of them added together. So we have 10J plus 6 plus 4J minus 10J plus 2, which is going to be 4 plus 10 minus 10. Or actually, I'll do the real part first. So 8, and then 10 and 10 will cancel, and we're left with 4J. Right? We all see that? Cool. And technically, this has like a unit of ohms. Now, to find the complex current going through here, V equals IR, this translates into V, oh yeah, and they use like a little squiggly thing for stuff in the frequency domain for some reason. Uh, but you just replace this with an impedance and the math still works. So if we want to find that complex current flowing here, right, it's just going to be our voltage over our impedance that we just found. So this is going to be 7e to the negative j70 over 8 plus 4j. Now, how do you do this? Well, you can either plug it into your calculator. If you look at the video that I posted on how to do that, make sure you like do it correctly. Or if you want to do this like the good way, which I think you're supposed to do on your quiz anyway, just to show understanding, is we're going to turn this into a e to the j theta form, and then based on the rules that we know if we have a1 e to the j theta 1 divided by a2 e to the j theta 2, then that's going to be a1 over a2 e to the j theta 1 minus theta 2. This is a combination of this is really just rules of exponentials. If you divide an exponential by another exponential, you subtract the power thing. And these are just coefficients, so they get divided. So anyway, to do this, if we think about it, right, I'm gonna draw the complex plane again because I think it's good to think about it in that form. If we have the real line and the imaginary not in line, there's no reason that I made this squiggly. I'm just bad at drawing. So we have 8, and here we have 4j, right? So this is our point in imaginary space. And we want to find out, okay, what is this a and what is this theta? So the way you can do that is I like to think, okay, we have a right triangle here, right? So you just do the Pythagorean theorem. A is going to be equal to the square root of 4 squared plus 8 squared, which is square root of 96, which is something. That's a 66, 96. Um, what is that? I'll just plug it into my calculator. Let's see. I'm sure you can. It's like, what is that? Like something times four. I don't know. I don't know. Square root of 96 is 9.79. It's like 9.8. Close enough. Yeah. 9.8. And then theta, based on trigonometry, because we all know trigonometry, is the inverse tangent of the imaginary part, right? Because it's the opposite over the adjacent. And the opposite is going to be the imaginary part, so just 4. And then the real part is 8, right? And then if we plug that into our calculator, 4 over 8, we get 26.56 degrees. One thing that I'll actually point out here is let's say we got this and it was actually like -8 minus 4j. So I don't know, let's say we were here. When you do this in your calculator, you'll still get a positive number here. So if you end up with a point here and both of these are negative, make sure you're thinking about whether it's supposed to be this or that plus 180. In this case, since both our oh, and same thing with like if you were here, you're the tangent inverse function on your calculator is always going to output something in this half of the plane. So it's always going to output something between positive and negative 90 or positive and negative pi or pi over 2. So just make sure you're thinking about which quadrant this is actually supposed to be in. Yeah. Like if this was -8 plus 4j, you'll end up getting like this angle. But really you wanted to get this angle. Yeah. So make sure you understand what it's saying in the complex plane. Like it's there's a reason I'm drawing it out here. So, now that we found these two, we know that 8 plus 4j equals or about equals because I rounded a bit e to the j 26.56 degrees. Now, kind of got sidetracked here. Right, we're here. So we know that the current is equal to 7 e to the negative j 70 degrees over 9.8 e to the j 26.56 degrees. All right. So, wait, I might have done math wrong here. Inverse tan of 4 over 8, and then did I do that? Oh, wait, I think I did. What's 8 squared? I think I did 8 squared plus 4 squared wrong. Oh, I so did. Okay. Yeah, it's not 96, it's 80. Oopsies. So then the square root of 80 is 8.94. So made that mistake, but we're fine. 8.94. Okay. Okay. Now we're here. As I said before, we evaluate this like so. So 8.7 over 8.94 is going to get us about 0.78. Or I'll write out the intermediate step. So we have 7 over 8.94 e to the j, and we have the thing on top, so negative 70 minus the thing on the bottom, 26.56. And if you look, these are going to add because they're both negative. So we end up getting 0.78 e to the negative j 96.56 degrees as our current. And so this is our complex. So this current here, right, is the current here, which is the same as the current here. So this is the current flowing through our 2 ohm resistor. So now all we have to do, because the question was asking us for it in the time domain, we have to take this number and turn it back into a I of, oh God. We're taking this and turning it into a I of t. And to do that, we just do here what we did, we just do it in reverse. So because the initial frequency was 100, it's still going to be 100. So now with this, we know that our I is that. So then we turn that into I 2 ohm of t is going to be 0.78. The amplitude stays the same. Cosine of 100t, because that doesn't change, minus 96.56 degrees. And that there is our final answer. Cool. Takes a while. The math is harder because it's complex numbers, but the like thought process is like really it's just 4 resistors in series and you divide the voltage by the resistance because V equals IR. Hopefully you're all clear on that. Don't get scared by the complex numbers. Just like try your best to turn them into imaginary numbers and then think of them as if they were resistors because in effect they are resistors. And then the process is exactly the same as what you did for the first half of this class. I'm basically going to be saying this every week for the rest of the class because you're kind of just doing stuff with complex numbers, but stuff you've already done, and you're just going to do that over and over again until the end of the semester. So hopefully you'll be good at doing complex math by the end of the semester. Also, technically, I should have put a uh, amps for time is greater than or equal to 0 here. Cool. Now, how much time do I have left? I have like 10 minutes. Okay. I'll do just to drive the point home, I'm going to do one more question here. Uh, this is another way you might see the this equals e to the j 0 degrees. So they sometimes use like an angle symbol for that, but it's the same thing. This is an example question where they are just asking you to do node voltage equations, but now you have imaginary numbers. Ooh, spooky. However, you'll see that it is exactly the same, and this question should take you maybe a minute if you get this on a quiz. Okay, we have. So sometimes also they'll give you the impedances already like found for you. So if you look at this question, right, it doesn't even like tell you what frequency you're at because it gives you the impedances already. Um, So this is just write all equations to find the complex current through the 4 ohm resistor. And for this looks like it would be pretty good to do node voltage on. So that's exactly what I'm going to do. We look at this, okay, what are our nodes? We have one node here, we have one node here, and we have one node here. I'll call this V1, V2, and V3. And we want to find this current eventually. And there's one dependent source, so we're going to have one dependent source equation. So overall, we have 1, 2, 3 equations, and then another equation for the dependent source, and then one equation to actually say what that current is through the 4 ohm resistor. So I'm just gonna write all the equations real quick right now. So at V1, technically V1 bar, if you're being fancy, we have V1 minus 90 over 3 ohms plus V1 minus V2 over J2 plus V1 minus V3 over 4 equals 0. Wow. At V2, we're going to have V2 minus V1 over J2 plus V2 minus 0 over negative J8 plus, okay, now we're looking here, same thing as before in previous weeks. We have V2 here, and so here, because there's a voltage source, we're going to have V2 plus 2I. So we have V2 plus 2I minus V3. This looks like a J. It's annoying me. Okay, there we go. Okay. Minus V3 over J6, and that equals 0. And then finally, at V3, we have V3 minus V1 over 4 going up, plus V3 minus V2 plus 2I, right? For the same reason I said above, over J6 plus V3. Oh, and actually, no, for this last part, since it's a current source, it's telling us the current is just that, right? So we don't even really need to write this part here. So this is just going to be, since the current is going into the node, it's going to be minus 530 degrees. And again, this is just like 5 e to the j30, which if you were to plot this on if you wanted this in a to the bi form, it would be 5 cosine of 30 plus j sine 30. And this is what, 5 times root 2 over 3 plus j times 1/2. And that's how you do the math there or whatever. But that's not important. I'm not teaching you complex math. Hopefully you guys know that. So we have 3 equations here, and then there's 2 more. We need to say, okay, what is I? So this current here is going to be equal to, okay, we already found that term. It's this one, right? Because it's going down out of V2. So it's just that. So we have I bar equals V2 over negative J8. And then finally, it was asking us what is the current through the 4 ohm resistor. Let's just decide that we're saying that it's going to the right. We don't actually know, but I'll just say for my equation, this is I 4 ohms. So for that, in that case, I of the 4 ohms is going to be V1 minus V3 over 4, right? Cool. And that is the whole question. So that's that's how you would do this. Very cool. Um, yeah. So again, it's like the numbers look scary, but it's just the exact same question that you've had before. I just wanted to drive home the point that it is still, you're doing the exact same math. It's just all the numbers are complex numbers now, so it gets scary. But it's still the same math. It's just now instead of having integers, you have complex numbers. Okay, I have 5 minutes left, which is not really enough time to do anything. Let's see. What could I do? Maybe I'll like start this question and try to talk through it. Yeah. Okay, so this is back to the time domain. This is the big table of equations. So we're going to start. Oh, and if we look at this, okay, just thinking about which equation set we're going to use. So after this moves away, right, this whole part of the circuit isn't here, and then we're left with these things all in series. So this is going to be a series question, series equation. So yeah, and we're going to end up finding a VC of t from it. Yeah. So here, again, we're going to start by just finding our VC of 0 minus and our IL of 0 minus. So our VC is going to be, well, actually, first let's look at, we know that our capacitor will be an open circuit, right? So it will end up, actually, okay, it's easier to first look at the inductor. So if we ignore this path because that's an open circuit, then what's the current through this inductor? Well, we have a voltage source. The path is like this, right? So our IL of 0 is going to be, if this is a wire, what is the resistance that this sees? We have a 4 ohm resistor and a 6 ohm resistor. So it's going to be, let me swap the order of these. So this is going to be that 10 volts over 4 plus 6, which is 1 amp. That's how we do that. Now we want to look at, okay, for this capacitor, what's the voltage that this capacitor sees? Well, if we have 4 ohms here and 6 ohms here, and this is a wire, we basically have a voltage divider where we see the voltage across here at the capacitor. Because remember, there's no current flowing through this 3 ohm here. So this is going to be 10 times 6 over 4 plus 6, which is 6 volts. So that's what our first thing is. Then when the switch gets moved away, we end up having this, which we can simplify by combining those two things in series there. We have the two resistors in series, right? They're not like next to each other, but since they're in series, we can pretend they are. So we have the R, or we have, yeah, I'll do it in order. So we have R, L, and C, and they're just connected like this, right? So it's going to be 6 plus 3 is 9. We have 0.02 farads, and we have zero point 0.5. This is not farads. This is Henry's. Oopsies. What did I do? Oh, what were the original numbers? Zero point 0.5 Henrys and 0.02 farads. Yeah, okay. So this is our final circuit. So now that we're here, we want to say, oh, and actually, we should try, I guess it doesn't matter all too much. Like it was given that this is the original voltage, but since things are in series, we can kind of just, it's kind of hard to think about which way the voltage will be. But give me a sec on that. So it's actually better to think about this up here. So we know for all of the series equations, let's copy the chart over again. I'll go through this question because I think it's good to go over. For the series equations, it does ask for IC of 0, right? So this is something to think about here. And for IC of 0, let's look up here. So we're not looking at this anymore. We know that IL of 0 is going to be 1 amp because we found that here and it can't change. If we have 1 amp flowing there, then after this switch moves and the capacitor is and it's disconnected from the rest of the circuit, we're still going to have 1 amp flowing around in this circle, right? So that means the capacitor at time equals 0 plus will have 1 amp flowing through it. Now, what is the sign of that amp? Well, if the capacitor has 6 volts across here, right? And we have current flowing up through it. Right now we have the current flowing with the voltage rise. So that means it's going to be negative because the positive is when the voltage drop is in the direction of current. So we're going to say that we have I C of 0 equals negative 1 amp. That's where what I was saying at the beginning can be confusing. Yeah. So now that we have that, we know that we can just label it like this. Now we have to figure out what equation we're using, and so we're going to just use that stuff from before. So we use the equations on the bottom. This is series RLC, so alpha equals R over 2L, which is going to be 9 over 2 times zero point 0.5, which is just 9. And then omega naught is going to be 1 over the square root of LC, which is 1 over the square root of zero point 0.5 times 0.02, which gets you 10. And if you see, that means omega naught is greater than alpha, because 10 is greater than 9. And that means we are using the underdamped equations. So this is the one with the sine and cosine. So we need to find our D1, right? So that means we're using this. So what is our D1? D1 is going to be VC of 0, which we found to be 6 volts, minus VC of infinity. If we look at this circuit here, right, there's no voltage source or current source in it. So eventually we know that as time goes to infinity, all the energy will be dissipated in this resistor and it'll all go to 0. So we know that VC of infinity equals 0 since there's no source. So it's 6 minus 0, which is 6, right? Now for D2, we need that omega D term. I honestly have no idea what that is, but they have an equation for it, so I'm using that equation. And it's 10 squared minus 9 squared. It's like the square root of 19, yeah, which is 4.36. Now for D2, we use the big equation. It's 1 over C, which is 0.02 times VL of 0, which we found to be negative 1, right? So plus alpha, which is 9 times D1, which we just found to be 6, over 4.36. And you end up getting 0.917. Now, finally, we go in and we just plug everything into the big equation. So let's see, what's the big equation? VC of t equals e to the negative alpha t times d1 cosine of omega d t plus d2 sine omega dt plus, I made this too big, or I'll move it like, ah, okay, here, yeah, this plus VC of infinity, which is plus 0 volts, 4 times is greater than or equal to 0. And so that's your answer. So again, it's like if you're going to get tripped up, it's going to be in the transformation from here to here and like thinking about the current at 0. But once you have it in this form, you really it's just equations and you plug in the equation and you plug in the equation and then eventually you get your answer. And yeah, it's annoying, it takes a while, but it's pretty straightforward if you know what you're doing. So yeah, that's it for today. I'll stop the recording here.